All right, hello over there. This is a cast sketch that I did that's 1/10 the scale. The hovercraft is about 4 by 1.9, which is about the average car size, which is 5 by 1.9 meters. As you can see, it's 1/10 the scale, so you have to multiply by 10 to get that amount, but you can do that and you'll get the same amount. Anyways, with that said, we're going to begin talking about how it's symmetric, which is gives the property of only having the diagonals matter for the moment of inertia. Well, it's not totally symmetric, but it's enough that it's like IXY, IXZ, IYZ is basically null and void. Um, and also there's some fluid mechanics trick I did over here where I cut over here a little bit so that there's some force this way and there's a force this way that tries to stabilize without control. And also there's a battery pack over here that you can see clearly over here that's removable. You can just snap in a new battery without charging because who wants to wait for a battery to charge, right? Anyways, that's a cool design over here. And then we're going to move on to the structural element over here, which if my, okay, let's do that. All right, structural element. The duct over here, as you can see, there's a little bit of structural element. First of all, we have to call upon Dr. Chi with the normal stress equations, which over here. With the skin equation here is from Dr. Kosmaka, and you can get this form over here, which we're going to now do a safety factor of 3. The important part over here is that we have put a safety factor of 3 which gives us that. Now we have the ultimate stress, but we're going to divide that by 4. And then we're going to plug into this now derived equation. With that said, we have some 32. This 32 is basically the amount of these lines we have over here, which is called a rib. We assume straight for simplicity, but there will be 32 of them. And with that said, we can get the thickness that we need, which is 0.05962. But because it's round, I'm going to round it up to 1 meter. And now we can get the mass of that, which is 15.38 kilograms. With that said, we're going to move on. All right. Anyways, next up is basically, if you look over here, is the rib structural analysis, which is pretty simple. It's just rib over here, stress analysis over here with the area over here. Basically, you get the pound, and you can see that the rib is less than the allowable, so we're fine. Then we get the mass of that, and we just have a structural wind. Structural wind is just extra. It is just in case, but you can get the mass over here, which is 18.93. We are in total gonna add a little bit more on it because 20 because of the extra joints I put in, aka these things you see over here that make it structurally viable. Um, which we have done the math over here, the same math over here where we do stress and we found stress is less than, and then we get the 0 point about 6, so 0.6 over 5. So we're just adding it to the 20 kilograms to make it easy for ourselves. All right, that section is done. So now next section is someone else's. No, this is my section, sorry. Um, then we do the structural mass. As you can see, we do all the math over here with the Excel table, and we get IXX, IYY, and IZZ. And with the frame joint cost, you can see about $15,547.2 that you had to spend on just the frame. This does not count for manufacturing and all the other stuff that counts to making that product possible, but it does cost a lot, as you can see. All right, now it's someone else's section. So yeah, I'm just gonna flip through them. All right, the next section over here is basically doing some matrix rotation because if you think about it, the thrust over here, we're moving the angle. So if you have, we'll show it off, but it's basically a cross product, but you'll see over here what it means. Basically, it's a rotational matrix of moving from IXX, the possible movement in IXX, possible movement in IYY, and that is basically the movement that we care about. Excuse me. And with that said, you can see by visual understanding that it does work. So for example, I like to do a little bit of a simple analysis where we have a beta equals 0. And if you have beta equals 0, you see over here that this is true. This angle has effect over here, sine and theta, which makes sense because if you look at that and do a parallel axis line theorem, you can kind of see where the moment goes. And so forth, so forth. All of these have the same thing. And if you do the math, it shows up and it's all good. Next up, we see over here the allowable, movement. The mass movement, I don't really give too much care about because mass movement we found out from the toy model is not really useful for unless it's a small perturbation. So we just stick it to 50 millimeters over here. Basically, we forced it to be 50 millimeters. This side over here can go to 10, but we just forced it to do 50 millimeters because it's um, sorry, 100, not 100 millimeters because it's times 10. Anyways, that's cool. Anyways, there's a lift coefficient over here, which is for the control vane, which is going to be plus or minus 10 to avoid stall. And we have a thrust vectoring that's about plus or minus 20 degrees because that is good over here. Actually, this thing can go more than 20 degrees, but we limit it to that because there's really no need to go any further, in my opinion. So here's a simulation. Here's the Fourier analysis. So I basically use Fourier series to get a perturbation, vibration perturbation over here that creates the zigzag situation. And it creates an interesting effect because it's Fourier series. So it has some interesting properties that make it so that it's symmetric, so it doesn't really go like crazy and go to explode. But in reality, but the controls do work in that sense that it does go into like a linear profile over here, and it does go for a linear profile over here, linear profile over here. Here's our guesses, here's some of the actuators. So basically, there's a global controls, which we're going to show a Bode plot soon. And then the global control, and then we have these actuators that to make it possible, they basically use a prediction model, basically least square, to see what is the best way to get to that control working. You'll see over here what I mean. Obviously, there's a lot of assumptions, so it's not very accurate, but it still works. And also, we can't linearize because of the cosine. Cosine is 10 degrees, so it doesn't work, as you know. And here's a global control variable for a Bode plot. And with that done, I'm done with my section. So, oh, and also I should probably put, um, here's the works cited, and here's all the professors that I used. Thank you.